of moduli space of sheaves on P2 today, okay? So let's start with the following things. So the Drezler-Potier classification of stable bundles on P2. Okay, so first, what you start with is that there's these things called exceptional bundles. So now what does this mean? An exceptional bundle is something where, you know, it's simple. So or maybe let me say a stable. So let me call it like this. E alpha is a stable bundle such that x1 E alpha is 0. So the way you should think about this is that this is this is the tangent space to the moduli space. Okay, so what this is saying is that it's a rigid stable bundle. Okay? So you see, one remark to make is that if you are on a surface like P2 where minus k is effective, then you don't have self x for x2s for, so let's make a remark generally here. Say you are on P2, send the V stable on P2, then you see x2 VV, let me in fact say it like this, xt VW is 0. Say that VW is stable, okay? And let's say that the slopes are close. And let's figure out what close means with close slopes. And that just means that the slopes are within 3 of each other. So then this x2 is 0. So let's do the calculation. So why is this? So this is HOM, right? WVK, right? Dual. So now what is this? So here we have the slope of this is the slope of W. The slope of this is the slope of V minus 3.
In this case, there is no polarization to define.
Well, P2 has only one polarization. Picard rank is 1. So that's why I'm not. So then you see, as long as this is bigger like this, right? Then you don't have any so that you see the point is that this x2 is 0, so this guy is equal to 0 if you have this. So in other words, if V and W are stable bundles on P2 with close slopes, and close means that if 3 is bigger than uv minus mu w, then this x2 always vanishes. So in particular, you know, if you have a stable bundle, it never has self x2s on P2. This is very special to surfaces where minus k is negative, right? So if you have a surface with minus k negative, this kind of thing, you know, there's a corresponding statement, and then what it means to be close is different, okay? All right. So now you see, so exceptional bundles will be things such that x1 E alpha is 0, but also x2 is also 0 because we are on P2, okay? So now what are some examples? So line bundles are an example, like O of 1 and so on and so forth. These are examples. And of course, once you have an exceptional bundle, if you twist it by any line bundle, it's still an exceptional bundle, right? Because if I twist, then the twists just go away. Okay, so then the next thing that you can do, here what you can do is you can look at the following. So let me do it like this. I have a map from O of 1 tensor HOM O of 1. I think I need to put the dual there, right? So that it's like completely canonical, right? So you take all possible homomorphisms from O to O of 1. So this secretly, of course, what it does is that O of 1 with 3 copies, right? And then what's the co-kernel of this? Tangent bundle of P2. So this is the tangent bundle of P2. And then you see this kind of thing is called a mutation. I mean, for the life of me, I can never know whether it's a right mutation or a left mutation or whatever, and you're not going to learn that from me. So you look in Rudakov's book if you want to figure out it.
Exactly the Euler sequence?
It is exactly the Euler sequence, but I want to look at it like this. So you do like, you started with an exceptional collection, like O of 1, O of 2. You take two adjacent ones, and you take all possible homomorphisms between them. And you look at the kernel or the co-kernel, depending on what you are doing, and such a thing is called a mutation. And then you see, I think this was an exercise, but we can check that TP2 is also exceptional. Okay? So TP2 is also exceptional. And now, you can keep going. I mean, I think maybe the way I want to do this is, you can keep mutating to get more and more exceptional bundles. So, like, for instance, if I have...
Stable.
What?
You mean that it's stable?
They are stable. It will turn out that all the exceptional bundles are stable, but you get, each time you do a mutation, then you get an exceptional. So now, for instance, I have a new exceptional collection, O TP2 of -1 and O of 1, right? So what I could do is, for instance, I could take this and this, or this and this, and make a new mutation, yeah? And then I'll get a new bundle, and that will also be an exceptional bundle, and so on and so forth. Okay? And the theorem here is that all exceptional bundles are obtained by a sequence of mutations starting by line bundles. So the little theorem here is all exceptional bundles are obtained from by a sequence of mutations, starting with line bundles. Okay, we are going.
Just to make clear, what is a mutation?
Mutation is you have a strong exceptional collection, like O of 1, O of 2, O of 1, O of 2. What you do is you take two adjacent pairs, you look at all possible homomorphisms between them. Mm-hmm. Like, you do the canonical evaluation map like this, and then the kernel or the co-kernel of that is the right or left mutation, whether it ends up in the right or the left, okay? And now you can keep going. Like, for instance, what I could do, you see, you have a map from O, right? So to TP2 of -1, this has 3 sections, right? So like, you get a map like this from this, and then there's some rank 5 bundle. So let's see, what's the slope of this thing? This is 3, so this is the 3/5 bundle. Okay? So this is the next mutation, and this is the next exceptional bundle. And now you can keep going, it's an infinite process. Okay? I'll tell you more about the possible slopes that occur as exceptional slopes in a second. Okay? Let's just sort of for now leave it at this. So now you see, if you have an exceptional, okay, so you see, say that you have an exceptional bundle. If E alpha is an exceptional bundle with slope alpha, then I know the rank and the discriminant of this bundle. Okay, then we know the invariance. Then we know all invariance. So now the reason is this. So first of all, let's look at chi E alpha. So this is the alternating sum of the x, right? Well, x1 is 0, x2 I told you is 0, so there's only hum, but the stable bundle, so hum is 1-dimensional. So this chi is equal to 1, right? On the other hand, by Riemann-Roch, this thing is like, is like r square. This is the rank of the bundle times p of 0, right? Minus 2 delta alpha. Maybe let me put an alpha here, right? So that you get that this guy is 1, but P of 0 is 1, right? This is the Hilbert polynomial of O, right? So you get that R squared is 1 minus 2 delta, R squared times 1 minus 2 delta is 1, right? So that, I can solve for the delta. What is it? That's a half times 1 minus 1 over R alpha squared, I think, something like this. So certainly, the discriminant is determined. But you see, the rank is also determined because what has to happen is that the rank and the C1 have to be relatively prime for you to get 1. Because I can write Riemann-Roch in terms of the R and C1. So you see, the rank by Riemann-Roch, rank and C1 are relatively prime. So that means that, the rank has to be the smallest number such that if you multiply the slope, you get an integer. Mm-hmm. So the rank is determined and the delta is determined, okay? Okay? So the slope determines all the invariants. That's the point that you should get, and that follows just from Riemann-Roch and the fact that chi E alpha is 1, okay? All right. Then the next thing to note is that if I give you an invariant, if I give you a slope, there can be at most one semi-stable bundle. There can be at most one stable bundle with that exceptional slope. So suppose that, so in other words, the moduli space of exceptional bundles is really one point. There aren't, you might worry that it's rigid, but there might be 5 points or something like this. That doesn't happen. It's just a single point. Because suppose that you have E alpha in E alpha prime, right? With the same invariants, two exceptional bundles, I won't say that they're the same, right? But where I said this, there are no x2s between them, right? But then you see what we know is that chi E alpha prime is equal to 1, right? Because that just depends on the invariance. It doesn't depend on what the bundles are. And I know that x2 is 0, right? E alpha prime, sorry, this prime is there. E alpha prime is 0, right? Because they have the same slope. So in particular, there's a hom. So you have two stable bundles with the same slope, and there is a hom, right? Non-zero hom, so then they have to be the same. Okay? All right. So it's really a single point. Okay. All right. Okay. So then there are these exceptional bundles. In some sense, you know how to find them. And I'll tell you a little bit more about what the possible slopes are. We know completely the classifications of the slopes. But now I claim that, so let's pretend for now that we've understood all exceptional bundles. And I claim that now the rest we can understand too. Okay? All right. Now suppose you have an exceptional bundle, E alpha. Alpha some exceptional bundle. Okay? And now suppose that you have some other stable bundle, V. Let's say that V is it could be semi-stable if you want, is a semi-stable bundle. Let's say that of slope mu, and then you see I can say less than alpha if you want. Let's look at the case for less than alpha, okay? But close, okay? But close. Alpha and mu are close, within 3 of each other. I don't want to look at really far away, but close to alpha. Okay? So then you see what this means is that let's think about what happens. I can't have any maps from E alpha to V, right? So I don't have any homomorphisms like this because this guy is stable and this guy is semi-stable of smaller slopes, so no homs. No homs. And similarly, you see there are no x2s because I said it's close and there are no x2s. Yeah? Plus no x2s. Because we're close. Close means always within 3.
No, but if you're considering maps from E alpha to B and the slope of
Alpha is bigger than mu, right? So I don't have anything to assume. No maps. No homs. No homs. No x2s, right? So it means that, you see, I can only have x1. I might or might not have x1. But what this means is that if I do chi e alpha to v, right, that has to be less than or equal to 0. We must have. Right? All right, so now let's write this thing down. So if we write this thing down, so I can use Riemann-Roch. So you have P of mu minus alpha minus delta of V minus delta of minus delta alpha, right? I mean, I've of course told you what delta alpha has to be, but let me not put it in. So this guy, so let me set this thing equal to 0. So you see that this delta of V has to be bigger than or equal to P of mu minus alpha. I mean, we can write this thing down. So it's mu minus alpha square plus 3 times mu minus alpha plus 2 over 2 square plus delta alpha. Okay? You get some quadratic polynomial like this. And similarly, you see I can do it the other way around, right? So suppose I have V semi-stable bundle with, mu bigger than alpha and close. By the same reasoning, then you have to have that chi V E alpha has to be less than or equal to 0, and you get a similar thing here. So that now you have that, delta of V has to be bigger than or equal to now alpha minus mu square plus 3 alpha minus mu plus 2 over 2 plus delta alpha. Okay? So in other words, what this says is that if you're thinking about the slopes and the discriminants, okay? If you're thinking about slopes and discriminants, if you have an exceptional bundle E alpha here, right, then there are two parabolas like this, right, such that if you have any stable bundle, the invariance of the stable bundle has to be higher than that. Okay? Right, that's what this reasoning says. And then, what you can do is you can draw all these things as you vary over all exceptional slopes. So let me draw the picture. This I'll call the Drezl-Potier curve. So let's say we have the Drezl-Potier curve. So let's make our thing. This is our mu axis. This is our delta axis. So here I want to put a half. So here I have O, right? So here is 1, I guess. So then you have this guy, the two parabolas like this. And maybe say that this is 1. So this is O of 1. So here you have O. Here you have O of 1. Here you have the tangent bundle twisted by minus 1, right? So here you have a little peak like this. Sorry, I'm not drawing these things to scale very well. And then here you have the 2/5 and 3/5 bundles that we saw, right? I had this 3/5 bundle. So then you have a little peak for those. And then, this is some fractal curve like this. Okay? It turns out that there is always a region where one of the exceptional bundles is the best one. And, so that you get a curve like this with, this is a fractal curve. And theorem of Drezl-Potier says the following thing. An integral Chern character R mu delta, I'm going to express my Chern characters in terms of mu delta, is the Chern character of a Gieseker semistable sheaf. If and only if R mu delta is exceptional, let me call this curve the Drezl-Lepotier curve delta, okay? Or delta is greater than or equal to delta of mu. Is above this thing. On or above. In other words, the theorem is that you have these exceptional stable bundles. The moduli spaces in those cases are just 1 point. Or any stable bundle lies above this, right? And furthermore, every integral Chern character is the integral Chern character of a stable bundle. So far, what I haven't proved for you is that last part, and maybe I won't prove it for you, but you can just construct it. I mean, the way you construct it is that you compute the Harder-Narasimhan filtration. And then the statement is that in the Harder-Narasimhan filtration, like, the destabilizing sub or quotient has to always be, either the sub or the quotient has to always be an exceptional. So then from there it follows that this is the picture. Okay, but anyway, I didn't do that part.
So you get the moduli is just 1 point for values.
Right. So one thing that I should have noticed that you see delta alpha is always less than or equal to less than a half here, right?
Yeah.
Right? So like the exceptionals always lie below the line a half. All other stable bundles are always above a half.
Yeah, and for
okay?
the moduli is
the moduli,
nice variety.
right, so there's more to this theorem. In fact, you see, like, let me just maybe say the other things. The moduli space is not only non-empty, it's irreducible. The moduli space is irreducible normal factorial of the expected dimension and then you see the Picard group of this thing has rank 2 if you're above the curve and rank 1 if you're on the curve. So the Picard group of the moduli space has rank 2, I mean it's Z2, rank 2 if delta is strictly bigger than delta mu, and rank 1 if delta is equal to delta mu. Okay? Sorry, I wrote it.
The expected dimension is x1.
The expected dimension is 1 minus the Euler characteristic.
Is what?
Yeah. 1 minus 1 minus 2. So let's see. So the Euler characteristic is 1 minus x. Yeah, so it's 1 minus the Euler characteristic. 1 minus the Euler characteristic. So the dimension is 1 minus the Euler characteristic. Okay.
And for those that are exactly in the curve, is the moduli space special? Or?
Yes, then they are given by Kronecker modules. Okay? I mean, maybe I'll say what the Kronecker module is in a second. Okay. Okay, is at least the statement of the classification clear? I mean, I hope you see why the conditions are necessary. I mean, and that to say that they are sufficient, you need to construct the bundles, but maybe I'll skip that part. Okay. All right. Okay. All right. So now what we want to do is we want to understand what is the effective cone of this moduli space, right? So in other words, I want to understand.
Is it a fine moduli space? Or it's universal?
No. I mean,
Never?
it's fine if and only if the rank and, I mean, it will be fine if the rank and, if the rank and C1 are co-prime. And otherwise, there won't be universal families in general. Not even locally.
Yeah, okay,
Yeah, right.
Yeah, but for co-primes, there is.
Co-primes, then it's fine. And it's smooth in that case. Okay.
And do you know something about the Picard shift?
Yeah, I mean, I think you can compute the Chern classes and things like this with that.
But about the stability?
Oh, whether that's stable? No, I don't. I mean, that doesn't mean that it's not known, but I don't know.
Yeah, because, I mean, for vector bundles we get the stability, so I was wondering.
I don't immediately know a theorem like that, but it might, I mean, this doesn't mean that there isn't a theorem like that. I just don't know it. Okay.
If I give you a stable Chern character, the general bundle has rank the denominator of right?
No, no, because I mean, you know, like if you have an integral Chern character like this, right? You can multiply the rank by any integer. Say that again. Let's ask your question again. Maybe I misunderstood the question.
I'm not giving you the Chern character. If I only give you the mu and the delta,
Yeah.
and I look at the...
You look at the corresponding point, yeah. Right, you need to choose a rank that clears the denominators, but you can choose any multiple of that rank as well. Right?
Yeah.
Okay. All right. There's something that I was going to tell you. I mean, there's more known about the moduli space. The general bundle is always stable and locally free and things like this. We know those kinds of things too. But I didn't put all those things in here. I should have put them. Okay. And I said that as factorial. Okay. All right. So now you see, here is the idea. So we want to make effective divisors on this thing, right? We want to make effective divisors. So remember, we had these Brill-Noether divisors. And how did we do this? So I want to make a Brill-Noether divisor on... And let me drop the line. There's only one class here. I'm not going to specify. So I want to make a Brill-Noether divisor on this, right? So what you do is you choose a W such that the Euler characteristic of V tensor W is equal to 0, right? And then, you know, in your moduli space with W, you choose a sheaf. I think last time we had G. And then what I want to do is I want to define dG, which is, you know, the F's in your MV such that, you know, H1 of F tensor G is not equal to 0. Okay? But the question is, when is this thing an effective divisor?
No, why you choose H1 instead of H0?
I'm happy to choose H0. The reason why I keep choosing H1 is because sometimes it's H2 and sometimes it's H0. But whichever one it is, like H1 is always jumping. So you can cover both cases at once. Right? I mean, if you have a bundle, if like the general cohomology is 0, right? Mm-hmm. And like, you know, it could be that the H2 is jumping or it could be that the H0 is jumping. Okay. Depending on whether your slope is positive or your slope is negative.
Yeah, but it's by Serre duality you have.
Yeah, sure, you can do that. Either you use Serre duality all the time, but I don't want to say that. So, I mean, I can cover both cases simultaneously by saying H1 is jumping. Because, I mean, you know, if H0, like, first of all, only one of them will jump. You can't, I mean, it won't be that both H0 and H2 will jump, just the special to P2. So, but whichever one it is, H1 will jump by the corresponding amount. That's why I always keep saying H1 so that I don't distinguish.
Okay.
But it's okay to do H0. Let's do H0. Okay? And then, you know, then if I do this, then I'll have to worry that the slope here is like positive instead of negative. Okay. I mean, but we can do that. That's fine. All right. Okay. But you see now the question is, when is this thing an effective divisor and not the moduli space? When is dG an effective divisor? Right? Okay, so here is the idea. Let's plot this thing. You see, I fix my V, right? I think of my W as a variable. right? So you look at chi v tensor blank, yeah? You see, I can plot this function in this mu delta plane. You know, there will be a parabola worth of w, so let's draw this thing. So it will be something like this, you know, it will be some parabola like this, right? Where this is the parabola chi v tensor blank, okay? And so that the question that you can ask is that basically for each of these points, right, each of the like rational or integral points on this thing, right, I have moduli spaces, right, and I can ask, okay, if I take the general member of this moduli space, is it true that you know this gives me an effective divisor? And then the question you can ask at which is the last point in here where you know you still get an effective divisor. Okay? All right. So now here is the fun part, which is, let me maybe spend 10-15 minutes on these fun things, because this is, you know, this is a beautiful thing that's worth mentioning. All right, so I didn't so far tell you. So here is the issue here, right? The claim that I want to make is that there is always an exceptional bundle that controls where this curve intersects the delta curve. So you see, I have my parabola, right? And I have my delta curve. So I want to understand how the delta curve and this parabola intersect. I want to say that it always intersects like this in some nice part of this peaks. Okay? The thing that you have to worry about is that this is a fractal curve, right? So if I subtract the good intervals, right, what's left over is a Cantor set. It's some uncountable, horrible thing. And you know, you might worry that this curve intersects the line and a half and a point of the Cantor set. Right? And what I want to say that this doesn't happen. Okay? So what to worry about? What we are worried about is that, you see, I have some Cantor set here, right? Right? And I'm worried that maybe my parabola passes through a Cantor set and I don't have a well-defined exceptional bundle associated to this parabola. What I want to say that if this parabola intersects this thing in a nice part of the peak, then there is a well-defined exceptional bundle associated to it. Okay? So the first claim is that there's always a well-defined exceptional bundle associated to this parabola. So we want to claim, so the claim is there is an associated exceptional bundle. Okay? All right, so let me tell, then I need to tell you a little bit more about the slopes of exceptional bundles, okay? So let's do it. It turns out that the best way to think about, there are two ways of doing this. There's various ways of doing this. So slopes of exceptional bundles.
And it can happen that the curve curls in one of the peaks?
No. No, it won't be able to do that. But I mean, because you know, these are. So the point is that these, I mean, you know, these are all translates of the same parabola. Okay, so I mean, one thing that I'm not telling you, I mean, this parabola is always like what's defining is the Hilbert polynomial of O, basically, right? So it's always translates of this. You're you're either shifting it or moving it up and down. So any two of these parabolas intersect at one point. And then you see, the point is that, and like, you don't have too many, like, if two of them intersect at one point, then, you already know that you've translated them and things like, you can figure these things out. It's not, we'll get to this. So let's talk a little bit about slopes of exceptional bundles. So there are various ways of doing it. So there's the Drezil-Potier description, which says that they are in one-to-one correspondence with dyadic integers. So there's a one-to-one correspondence. So these are exceptional slopes. Exceptional slopes, let's call it the set of slopes, yeah? They are in one-to-one correspondence with dyadic integers where you define, this map is called epsilon. Epsilon of n is equal to n, right? And, you define alpha dot beta. This is the mutation action. If I have two slopes, alpha and beta, I can take their mutation. I can compute the slope of that. Is given by this. It's alpha plus beta over 2 plus delta beta minus delta alpha over 3 plus alpha minus beta. Okay, this is a computation that you do. And so you see, for integers, I just send it to the integer. If I have a dyadic integer of the form 2p plus 1 divided by 2 to the q plus 1, then this is defined as the dyadic integer of p over 2 to the q by the same dot of p plus 1 over 2 to the q. Okay? So this inductively defines for you what the slope is. This is one way of doing it. It turns out that the way I like doing this is that you look at the continued fraction expansions of these things, okay? So this is the part that I like. Continued fraction expansions. And then you see, one thing that I didn't say, of course, these slopes are in, if you take an exceptional slope and move by 1, then that's also an exceptional slope. That's just tensoring by O of 1. Or if you flip across this axis as an exceptional slope, that corresponds to basically taking the Serre dual and shifting. So that you see, it's enough to describe the slopes between 0 and a half. Right? And then you get all of them by flipping on. So let me tell you, so everybody knows what continued fraction expansion is. That's like when you write your thing as 1 over a1 plus 1 over a2 plus 1 over a3 and so on and so forth. Okay? So that's the continued fraction expansion. Well, we have O, which is 0. Okay? Which I'll take it to be empty. In that case, we don't have anything. Then we have the tangent bundle, which is a half. Right? Tangent bundle twisted by minus 1, which is a half. And you can write that as 2 or 1, 1. Right? 1 over 2 is a half, or 1 over 1 plus 1 over 1 is a half. I mean, each rational number has two continued fraction expansions, right? You have an even length one and an odd length one. So let me write it like this. Okay? Then you see what I do. I take the even expansion here, and I take, the odd expansion here, and I concatenate them by putting a 2 in between. So the next one that I'm going to get is 2, 1, 1, or 2, 2, right? So this is by doing the mutations like this, and this is the 2/5 bundle that we talked about. Okay? Well, now I can keep doing this. So you see, I can get this one and this one. Again, I take the the odd one here. So let's see, which one do I want to do? Let's do it correctly. Yeah. So I have the 2, 2 here. I take the. Oh, sorry, I didn't. I should have written the 2, 2 down here. So you see, what you do is you take the even length expression here and the odd length expression here, and you concatenate them, putting a 2 in between. So I take 2, 2, I put a 2, and I concatenate with this. Or you have the odd expansion, which is 2, 2, 2, 1, 1, right? This corresponds to the bundle 12 29. That's another exceptional slope. Or I could have done it with these two, right? So again, you take, so then I get 2, 1, 1, 2. Again, I take the odd expansion downstairs. I take there is nothing there, so I put a 2. Or you can have 2, 1, 1, 1, right? Which is, that corresponds to 5/13. Okay? And you can keep going like this. So for instance, the next one I get, I can do like this. So I get 2, 1, 1, 1, 1, 2, or 2, 1, 1, 1, 1, 1, 1. I'm not sure that I wrote what the actual integer is at that point. But so, you can take these two and make, 2, 2, 2, 1, 1, 2, 2, 1, 1, 2. Whoop. Sorry. What happened here? 2, 2, 2, 1, 1. 2, 2, 1, 1, 2. I have too many. No, this is not quite right. What happened here? Oh, sorry. I missed. This is what I want to do. So I take 2, 1, 1, 2, 2, 1, 1, 2, 2, 1, 1, 2. Or, of course, 2, 1, 1, 2, 2, 1, 1, 1, 1. Again, I don't need to write all of these things down. So I can do these. I have 2, 2, 2, 2, 2, 2. And I can do these, which is whatever. 2, 2, 2, 1, 1, 2, 2, 2. Okay? All right. So and you can keep doing this. And the theorem is that this is how you get the continued expansions of all the exceptional bundles. Okay? Now, what do you notice about these things? So the things that you should look at are these ones. The even expansions. What are the numbers that they have? First of all, they only have 2s and 1s. There's nothing other than 2s and 1s, but they're pretty special as well. What's so special about them? They are palindromes. Like whether you read it like this or you read it like this, you get the same. Right? So what you get is that you get certain palindromes with, made of with 1s and 2s. Okay? All right. So then here is the theorem, actually, like the theorem that you have to prove. So this is with Jack and Matthew. It's that if you have any point on this Cantor set that we are worried about, so any point at the Cantor set is either an endpoint of these peaks, an endpoint of one of these peaks. So you have these peaks. It's exactly where the exceptional bound, like this delta is equal to a half along this peak, in which case it's a quadratic irrational or transcendental. So it's a transcendental number. Okay? And then, of course, then this claim follows from this theorem, because you see, like this thing is a quadratic formula. You are a quadratic equation. You are setting it equal to a half. So, the thing has to be a quadratic irrational. It's, again, easy to check that they can't intersect at the end point, because you have, two translated things. If they intersect at the end point, they have to be equal. Okay? So now how do you prove a theorem like this? It turns out that this goes back to these rote approximation type things. There's a theorem of Bugeaud and Adamyevsky, I think, which says that if you have a number whose continued fraction expansion has arbitrarily long palindromes, as it will be in this case. So, the way you should think about this is that, okay, I have some point in the Cantor set here, right? I can approximate that point in the Cantor set by these exceptional numbers, yeah? Well, I mean, what I just told you is that these are palindromes and they're arbitrarily long palindromes, right? So then the point is that if you can if you have a number and it starts with arbitrarily long palindromes, it either is repeating, in which case it's a quadratic irrational, or it's transcendental. And so now you know that it's transcendental.
And all the numbers of that kind, they appear in the...
Say it again?
For all the palindrome numbers, they appear...
No. I mean, you see, the set of palindromes...
Construct one.
No. You see, the set of palindromes that occur, right? It's hard to characterize the set of palindromes that occur. And then, you know, what it means is that you have to keep being able to break it into pieces by subtracting 2's, and each of the remaining pieces have to keep being palindromes, so to speak. Okay. So before I go on, there is a famous problem of number theory here that people should know as well, okay? There is another way of thinking about the slopes of exceptional bundles, so let me tell you that as well. And that's the Markov equation. So, you know, the Markov equation is like this: x squared plus y squared plus z squared is 3xy, right? X, y, z, yeah? And then this question is, there's a one-to-one correspondence between integer solutions of the Markov equation and exceptional slopes. So there's a correspondence. This is due to Rudakov, correspondence between integer solutions, or maybe Gorodensky and Rudakov, integer solutions and exceptional slopes. I believe if you take two of these consecutive things, two of these consecutive numbers, and if you have like a1 over r1 and a2 over r2, if I remember correctly, it's something like this. Then R1, R2, and R2A1 minus R1A2 is the solution of the Markov equation. So, you know, these solutions start like 1, 1, 1, 1, 2, 5, you know. So, you know, we have the 513, so, you know. So all the Fibonacci numbers occur, for instance, in here. And you have all the Pell numbers that occur with things like 2/5, 12/29, and so on and so forth. Okay? So you can do it like that as well. And then here is the conjecture, I think due to Markov actually. So the conjecture is like this. Maybe this is the reformulation by Rudakov. So that if, like, you know, a rank R can be the rank of at most one exceptional bundle. Exceptional bundle with slope between 0 and a half. So if I give you a rank, I mean, there might, of course, not be any exceptional bundles with that rank. But if there is an exceptional bundle with that rank, with slope between 0 and a half, there's a unique exceptional bundle with that rank. So that as I do this process, ranks never repeat. I mean, this is not the original formulation of that Markov had, because he didn't have exceptional bundles, I don't think. But so let me tell you, the original thing is that it says that, you see, I might as well always assume that z is bigger than y is bigger than x, because it's symmetric. So then you see, if you take the biggest one, and in fact, I think it's known that unless you're in 1, 1, 1 or 1, 1, 2, then they don't repeat. Like, so I think maybe you can even do this, right? So say that you have z, two solutions like this. So the y prime and the x prime and the yx are different potentially, but z is the same. If these are solutions of Markov equation, then y prime is equal to y and x prime is equal to x. So there's a unique such solution if you specify the largest one.
That's surprising. Yeah.
It's a surprise. It's been open for more than 100 years. It's a surprisingly annoying conjecture. Anyway, but maybe one of you will solve it by the end of the talk today. So. All right. Okay, but all of this was to tell you that, I have a well-defined exceptional bundle. Right? I mean, I went through all this number theory. All I wanted to say is that this parabola never passes through any of these Cantor set points. It really passes like this. Okay, so I have a well-defined exceptional bundle associated to this parabola. Okay, so now let me erase this. This was a number theory. By the way, I mean, there are many books written about this Markov equation, and Frobenius already has a book, and then, yeah, I mean, he was interested in the hyperbolic geometry of this equation. I didn't know this at the time we wrote the paper, so we had to rediscover some of these things known to Frobenius, He was a smart guy, so. All right, so then you see, then there are several possibilities. So you see, you have this peak, you have this exceptional bundle E alpha. And one possibility is that, of course, this parabola, you can be, I don't know, extremely lucky or extremely unlucky, however you want to say it, but the parabola can actually pass through the exceptional bundle. In fact, the examples that I did for you yesterday when we were doing 3 points, 6 points, or 12 points, it actually passes through that. But that's not typically what's going to happen, right? I mean, but as you move this parabola, it's very unlikely to pass to that point.
Yeah, but then you can always move it, no? Pass through that point.
Well, I mean, you need to change what your V is. I mean, you see that it's a pretty special situation where it passes through that. Except that, of course, every example I gave you yesterday was an example like that. So I'll call this one. And in this case, let me call this mu plus delta plus. Okay? The second possibility is that, say that E alpha is here. This thing can pass underneath like this. This is mu plus delta plus. And then the third possibility is slightly different. Let me do it like this. Here is my E alpha again. This thing can pass above, but go like this. So this is mu plus delta plus. I mean, you see this, I'm saying it can pass through, it can pass above, can pass below. What that means is that, of course, like, if you write your chi v, if you take, let me just call the Chern character of E alpha alpha, right? That's the case where it's equal to 0, is bigger than 0, and less than 0. That's what it means.
So I don't understand the third drawing.
Okay, so this is my peak. Right? This parabola is passing above the point, so that I suppose that the Euler characteristic that this thing is positive, bigger than 0, right? That pairing is bigger than 0. Then what you do is you extend this parabola and see where they intersect. Okay? And I call that intersection point mu plus delta plus. This is mu plus delta plus, and that's mu plus delta plus. When it happens that the exceptional is orthogonal, then you call that point mu plus delta plus. When it's negative, then you take what is this? This is my right hand. This is the right hand side of the thing. And when it's above, you take the left hand. I mean, of course, it could be that it just passes like this, in which case this is mu plus delta. You might not need to extend it, but sometimes you need to extend it. Okay? All right. So then here is the theorem. this is again with Jack and Matthew, which says the following thing. Let R plus be sufficiently large and divisible and G a general point general point of M R plus mu plus delta plus. I mean, of course, I need to make R plus sufficiently divisible, like so that, you know, it clears the denominators of mu plus and delta plus so that you get an integral. The other thing that I should say, you know, these points, of course, intersect at integer points because, you know, like, you know, you have integer parabolas with the same leading term, so those cancel as you're really solving linear equations. Then the Brill-Noether, then let me say it like this, then the cohomology of F tensor G vanishes for the general F in your moduli space P2V, and furthermore dg, so that dg is an effective Brill-Noether divisor. Which is extremo. Okay? So let's understand sort of what this means. So let's lie first, okay? It's good to lie occasionally. So let's ignore this case where you have to extend this thing a little bit. Like, ignore that you had to do that for a second, okay? What this is saying is that, you know, you look at this parabola, which is the orthogonal characters to V. And what this is sort of roughly saying is that the last stable bundle on that parabola is what gives you the extremal effective divisor, the Brill-Noether divisor with respect to the last possible stable. That's of course false because of this case where you have to extend it. Okay? But you know, roughly maybe that's how you should think about it. Okay. I mean, what I said literally is false, but you know. But maybe it's sort of more helpful than. All right, so now what is it that we need to do? Okay, so maybe I'll explain like how you approach this thing a little bit, what the point is. And you know, we were talking about so, and there's another way of phrasing the theorem, and let me rephrase the theorem.
Yeah, I mean, at the end you're saying that for the general G and F, the cohomology vanishes.
That's right. Yes, that's what I'm saying. And I tell you which G to take.
Okay, and I mean the generals, so the main thing is to look for the special ones, that in this case are going to be the exceptionals, or?
No, I mean, you know, I'm not making any claims about special bundles. There will be plenty of bundles that have like cohomology. I mean, potentially. So what this is saying is that if you have a general set of points in the plane, for instance, right, then you can find, then, you know, there's some bundle you can find by doing this process such that the Brill-Noether divisor with respect to that one will be the extremal thing. But of course, there will be many points, like points on the line, points on the conic, or whatever, that will have plenty of cohomology. So that's just a statement about the general one. So there is another way of saying this theorem in terms of Bridgeland stability, and this is what it says. You know, the general sheaf, and let me get this thing right. Do I have to put a minus sign or not put a minus sign? I always get confused about this thing. Yeah, I think I need to put a minus sign. I think that's right. So I think it's like this. The general sheaf F in MP2 of V is destabilized. Now this is in the sense of Bridgeland. Okay, so I have this E alpha, right, by the exceptional bundle E minus alpha, I think. By the exceptional E minus alpha. I hope I remember this completely correctly, but anyway, there's some exceptional that you get from this thing. Okay? So that's another way of thinking about this if you want. All right, so maybe what I'll do is maybe very briefly tell you what is the idea that goes into this. And then I promised Leticia that I would do some examples of matching Bridgeland stability and geometry. So maybe we do that, okay? Instead of spending too much time on proving this. But the idea is like this. You see, this exceptional bundle, like choosing this exceptional bundle, tells you which resolution you should get. So you see, the idea is this. So you see, I take a bundle G, a general bundle G in this thing, yeah? I mean, in general, it's very hard to prove that the cohomology of such a tensor product is zero. But the good thing is that there is a special exceptional collection that you make from this E alpha, right? And with respect to that exceptional collection, you know, G has only two terms. It's actually orthogonal to this E minus alpha, right? And then you can hope that F tensor, those two things have no cohomology, and now you can actually prove that the cohomology vanishes. So the idea is this: you need to choose a good resolution. Need to choose a good resolution. And this associated exceptional gives you an exceptional collection to use. The associated exceptional gives you a good exceptional collection. I mean, the point is like this. You see, like, the point is like this. Say that you choose the Gaeta resolution for F, right? If you choose the Gaeta resolution for F, right, then F will look simple. Like, you know, we'll have only three terms. But then there's no reason why G, in terms of those terms, should look simple. It will be some completely crazy thing. Yeah. And then you can't tell what the cohomology is. And similarly, if you choose, you know, your favorite resolution for G or something like this, there is no guarantee that F should look good. But now what we want to do is that the fact that you have this E alpha is going to allow you to choose simultaneously good resolutions for this thing in terms of the same thing. And then the orthogonalities will allow you to tell that the cohomology vanishes.
Yeah, and actually I think that, for example, you can choose a resolution in such a way that the cohomology is precisely some number, for example. No? I mean, what you're saying is that you are choosing the resolution in such a way that the cohomologies are non-zero. But for example, you can choose that.
No, I'm saying that they are zero. I don't know how to make them non-zero.
But then
it's really hard to control.
can you choose in a good resolution in such that, for example, the sub has some number of sections, and of course then you have the bundle that has.
I don't know how to do that. I think that's, I mean, you might be able
Really?
to, but I don't know how to do that.
Because as you say, the main problem is to choose a good resolution.
I mean, but I think the problem, like the moment these things are not zero, then it's a question of what's the rank of the map between them and how on earth are you going to figure that out. I mean, like, obviously this statement is independent of the resolution, right? If I choose the gaeta for F and use the same for G, right? I mean, then the statement is that, okay, you'll have some tensors with these things, so then, there will be some H naught in here, some H naught in here, and they will have the same rank, and then the statement is that the map is an isomorphism. But, I know no way of computing the ranks of those maps unless everything is zero, right? I mean, sure, in any given case, you can put it in the computer and it will spit it out, but I mean, how do you prove infinitely many statements like that?
No, I mean, I was just because it's possible to choose a good resolution.
Sure, I mean, it's possible, maybe you can choose a good resolution, you can do that, but I don't know how to do it.
Okay.
I mean, it doesn't mean that you don't know how to do it, it just means that I don't know how to do that. Okay, so then the associated exception gives you a good exceptional collection to use to resolve these things. Resolve, okay? And then, of course, you can use the orthogonality relations among these exceptionals to say that the cohomology vanishes, okay? All right, so maybe I'll say this much about it, and then you can read the details in the paper, okay? All right, but let's just, let's go back and in the remaining 20 minutes or so, do some examples of how do you see what happens. Are there any questions about this?
Yeah, I have a question.
Yeah.
I have one, as always. In the theorem, R has to be like sufficiently large and
Yeah.
divisible, but I could be naive and think that the denominator of mu plus might work. Do you have an example in which it doesn't?
I don't think I have any examples of that. That's possible, but then I don't know how to prove that statement.
Okay.
I mean, at some point you need to do some dimension count to say that something wins. And you need to sort of make it large.
Yeah, I understand that the proof is easier. Like,
Right.
But, okay.
And because it doesn't change the class, then, I mean,
Sure.
yes, you can ask that question. You just want the R plus that makes this an integral Shorn character.
Or minimum one by like that matter.
Yeah, I don't have an example, at least immediately, where that doesn't work. Let me make one more remark. Yeah, I think in the theory of curves, this things comes up a lot, right? So like you have a moduli space, right? So I have a moduli space M, MV, and I have the moduli space MW, and you get some rational map that sends FG to F tensor G. And then here you go to M, maybe I should make this rational, MV tensor W, right? And here you have the theta divisor because I rigged this thing to have Euler characteristic 0, right? So let's write that down. Yeah, so the question that sometimes comes up, is it possible that the image of this thing lies in the theta divisor, right? And here is a lot of examples where that happens, yeah? So the point here is that, you see, I'm saying that the extremal divisor happens here. But there are many, many moduli spaces in this region that still satisfy that I can choose my W's from there. And then, in those cases, what happens is that the image has to lie in the theta divisor. So you can actually see those examples all come up.
That's good.
Yeah? Okay, that's all right. Okay. All right, so let's do some examples of Bridgeland stability and correspondences between Okay, so let's do maybe a few simple examples and a few complicated, one complicated example. All right, let's do several numbers of points. So I'll do this only in the Hilbert scheme. So n is going to be equal to, let's do this. N is going to be equal to 3, n is going to be equal to 4, and maybe let's erase this thing and do n is equal to 7. So I'm on P2. I have 3 points, 4 points, and 7 points. And what we want to do is we want to understand, what are the various birational models of these things and what happens in Bridgeland stability. So let me tell you, like, if you look at the Hilbert scheme of points, right, then let's first tell you that let's choose a basis of our Picard group so that we know what it is. So I'll use H and B, okay? So B is the divisor of non-reduced schemes. This is the divisor of non-reduced schemes. So if you want, there is a map from P2N to the symmetric product, right? This is the Hilbert-Chow morphism. Hilbert-Chow. What it does is that it takes a scheme and it just sends it to support counted with multiplicity. Okay, so this is the symmetric product. And what it is that this map contracts the divisor B to the, to the singular locus of this, or if you want, repeated points. Repeated points is codimension 2 here, and what lies over that. It's an irreducible divisor. You need to know some theorems to know that. But, okay? And then H is the locus of points whose support intersects a line. So this is the locus of schemes whose support intersects a line. Okay, so you have n points, one of the points lies in the fixed line. Okay? If you want, it's the pullback of O of 1 from here. Okay. All right? And then let's repeat what we said before. If you take any degree D, then you get a map from the Hilbert scheme of n points. In general, it's a rational map to the Grassmannian of, H naught of OP2 of D. That's my vector space. And here you have, D plus 2 choose 2 minus n. Right? Let's assume that n, n should be less than this. You fix the D plus 2 choose 2 should be bigger than n otherwise. That's so interesting, yeah? So what it is that, you send a scheme Z to the subspace H naught of I Z of D. Okay? And in general, it's only a rational map because if the scheme does not impose independent conditions, then it might, and then the one thing to remember here is that, if D is bigger than or equal to n minus 1, this is a morphism. This is a morphism. The reason being that, a scheme of length n imposes independent conditions and, curves of degree n minus 1 or more. Right? If you think about it in terms of the resolution of the Z, right? The worst resolution that can happen, you have O of AIs mapping to O of BIs, right? going to IZ, if you look at the minimal free resolution, the least that BI can be is minus n, and that happens if and only if the points are collinear.
The points are what?
The least that BI can be, like BI is bigger than or equal to minus n minus 2, and equality if and only if the points are collinear, in which case you have O minus 1 plus O of, sorry, minus n minus 1, O of minus 1, O of minus n going to O of minus 1 minus n, right? Otherwise, this number is smaller. And now if you tensor this thing with something n minus 1 or bigger, then there is no then there is no H1, you can see. Okay, anyway, all right. What this means is that if you want, what it says is that n minus 1 H minus B over 2 is nef but not ample. We also get that H is nef but not ample. Okay? H was the pullback of this Hilbert-Chow morphism, so it contracts this divisor. There's some curves that are in, so it's nef, it's base point free, but it's not ample. And here you get a morphism to this Grassmannian in this case by looking at d equals n minus 1, but it contracts the locus of points that lie on the same line. Right? Because if you have n points on the line and you want degree n minus 1 curve, you have to contain the line. It's still the correct dimension, so you get the map, but you can't separate the things. So what this says is that the ample cone is always known in these cases. Here you have an H, here you have a B, so this is the extremal edge of the effective cone. Here you have an H minus, sorry, in this case you would have 2H minus B over 2. And here you have H, here you have B, here you have 3H minus B over 2. Okay? All right. So what we are saying is that here is the ample cone, here is the ample cone. B is always one extremal edge of the effective cone because it's a divisor that gets contracted by a rational map. Okay? Or if you want, there are plenty of curves in this Hilbert scheme that don't intersect B. Okay, so then the question is, what are the other rays here? I've told you what the extremal ray is in some sense because I just described what the theorem is. If you were to use what the theorem does in 3 points, you would see that it would pass through O of 1, this thing, right? It would pass through O of 1, and so this is, the extremal edge of this thing is given by H minus B over 2. H minus B over 2, and this corresponds to collinear, 3 collinear points. So this is 3 collinear points. Okay. All right, so now what happens in the case of, let's look at in the case of Bridgeland stability. I don't put my You see, in the case of Bridgeland stability, what happens is like this. So you ask what are the destabilizing objects, right? So I have my IZ and I want to know what are the destabilizing objects. It turns out that it will turn out in all the cases, the largest wall is given when you O of minus 1 is the destabilizing object. So the largest wall is given when O of minus 1 is the destabilizing object. But you see, O of minus 1, you have a map from O of minus 1 to IZ if a non-zero map, if and only if Z is collinear. Right? I mean, I have a non-zero map from O of minus 1 to IZ means that, Z is collinear. Right? So you have a non-zero map like this if and only if Z is collinear. And then what you get is that, the largest wall is the wall corresponding to O of minus 1. Okay, some semicircle. We can work out what the thing is, but let me not bother you with.
It's a finite number of walls?
It's a finite number of walls in the case of P2. So one thing that I should tell you, okay, let me explain. So the moduli space of sheaves on P2 is a Mori dream space. Okay? I mean, this is true on any Del-Pezzo surface if you want. It's a Mori dream space. So then what that means is that the Mori walls, you know, there are only finitely many walls where the thing changes, okay? And then the other thing that's true for P2 is that there's a one-to-one correspondence between the Mori chambers and the Bridgeland chambers. And it's a very explicit correspondence. I didn't explain this last time. I should have probably explained that, but there's a one-to-one correspondence. Okay? And then the next wall here is O of minus 2. Or maybe IP of minus 1. Doesn't matter. IP of minus 1. Okay? And then what this means is that you get a map from IP of minus 1, but you see every Z has a map from IP of minus 1. Right? I mean, you take your 3 points, you pick one of your points to be P, then IP of minus, you know, the IP of minus 1 maps to this thing because the remaining 2 points are on the line. Yeah? And then I should have written the centers of these things, which, I mean, it's written in the paper, but I somehow don't have it here off the top of my head. Okay? All right, so this is the first picture that can happen. All right, so then the next things that can happen is that you see, what happens is that if 4 of the points are collinear, right, then you run into the, you run into the thing that, you know, so first what can happen is that 4 of the points are collinear, right? Then the next thing that can happen is that you can have 3 of the points are collinear. So like if n is 4, right, let's go here. If n is 4 and I take d to be 2, right, then what happens there is that, you know, okay, if 4 points are collinear, then they don't impose independent conditions. But even if 3 of the points are collinear, they impose independent conditions on connex. But you see that locus contracts the locus of 3 points on the line. Because, you know, I can move the 3 points on the line, right? And then connex don't know about it. All connex contain the same line. Right? So then the next divisor, then you have something interesting happening here as 2h minus b over 2 here. All right? And then I told you what the effective cone is, and this is h minus b over 3. Okay? And then again, the Bridgeland picture is similar. Maybe the one that I should work in detail is n equals 7 because I have all the so let me draw first what the thing looks like, and then let's explain what happens. So here, there are a lot of them, so I have to not draw it to scale a little bit. So this 6, 5h minus b over 2, then I have 4h minus b over 2, then I have 3h minus b over 2. So then here you have, sorry, it's hard to draw it to scale. It's going to be like this. So this h minus b over 6. So I think the other two that I have here, h minus 5b over 24, and h minus b over 5, but I should put, let's divide this thing by, so let me write it like this. Let me multiply this thing by 12 and divide it by 5, so that I write it like this. Okay? Okay. All right. So now let's understand what happens. Again, this is the ample cone. Sorry, it's I mean, you know, this should be something like this, but I put it like this so that we can put the numbers in. So the way you should think about it, this is the ample cone. the first thing that happens when you have your 7 points is that they fall. They could all lie on a line, right? And then you see what can happen is that the corresponding Bridgeland wall is like, you know, O of minus 1 can destabilize some of the points. That means that you have a map from O of minus 1 to IZ, and that's the same thing as saying that the points lie on a line, okay? Then the next thing that can happen is, and then, you know, like 7 points impose independent conditions on curves with degree 6, so that you have this map like this, right? But, you know, they can't separate the collinear points. Okay? Then the next thing that can happen is that the quintex, right? You know, seven points such that no more than 5 of the points lie on the line impose independent conditions in curves with degree 5, right? Yeah. But they can't separate them. So you get the next wall, which is IP of minus 1. So that, you know, but to say that you have a map from IP of minus 1 corresponds to saying that 6 of the 7 points have to lie on the line, okay? Well, then you get to the quartic, the degree 4 curves. When is it that they impose independent conditions on quartics? Of course, if you have 5 of the points, you impose independent conditions, but you can't separate them. So that sort of corresponds to having, let me write it, IPQ of minus 1. So that says I mean, of course, this could be a schema of length too, but let me just write it like this. So, you know, then the next wall that you get is what corresponds to like having all but 2 of the points on the line. Then now when you come to cubics, right, then 2 things can happen, right? Either 4 of the points can lie on the line or all 7 points can lie on the conic. So if you have the 7 points lying on the conic, you still impose independent conditions, so to speak, on cubics, but you can't separate the points. And similarly, if you have 4 points on the line, you still impose independent conditions in cubics, but you can't separate it. Here, actually, 2 walls coincide, so to speak. Let me maybe draw it a little bit thicker like this. And it corresponds to having O of minus 2 mapping to your thing. Either 7 of the points lie on the conic, or PQR of minus 1. Right? So that says the 4 of the points are on the line, or 7 of the points are on the conic. Okay? Well, then, of course, the extremal divisor here, you can think of it as like 6 out of the 7 points lie on the conic. Okay? So the next thing that can happen is that we need to understand what this divisor is. Yeah? And I mean, what it is that in this case, you look at basically, you know, a bundle with slope 5/2. So in other words, it should be the tangent bundle twisted by 1, right? And you look at 7 points that fail to impose independent conditions on those. Right? You can describe when that happens, and that's precisely when 6 of the points lie on a conic. Again, this is the kind of accident that you were asking about last time, I think. You know, in general, saying that, you know, some number of points fail to impose independent conditions on the bundle, that's it. You don't have any other description. But, you know, this is one case where actually you do have another description. That's when 6 of the points lie on a conic, so that you see the next wall is IP of minus 2. And finally, we have like the last guy. And the last guy is just, you know, points that fail, it's like points that fail to impose, yeah, I mean, the last wall is given by, you know, it's TP2 of minus 4. That's the destabilizing guy, and this is what I've described by the theorem. Okay? So this is how it's going. I mean, you know, while some part of this is fairly standard, you know, for a long time, you know, what happens is that the interesting parts are like points lie on a line. Yeah. Then for a while, points lie on a conic. Then once in a while, you start getting things like points fail to impose independent condition on the tangent bundle. And then, of course, as you go further and further, then it will be like points that fail to impose independent conditions on some bundle. Okay? Okay? And then correspondingly, you know what the sort of destabilizing objects are. And this theorem is that there's a one-to-one correspondence between the Brisbane walls and these walls.
That's
Okay, and you can work out what happens. Okay? I mean, of course, as you increase the number of points, then it gets worse and worse.
Yeah.
I think we wrote down every single thing up to 9 points or something like this in the paper. I mean, there are tables. I forget now where we stopped, but and we managed to get it through the referee. I mean, usually the referee says, like, oh, this is all examples, take it out. Not this one, not this one. So, I mean,
Maybe ignorant question.
yeah.
In that paper, this correspondence between Brisbane walls and Warren walls is stated as conjecture. So
In what paper is it? I think in ABCH, we sort of proved it up to, some part.
Yeah.
And then say that it's always like that. Then, we check the effective cone, we check the monomial schemes and things like this. Then I think Chunyi Li and Xiao Lei Zhao proved it in general. I mean, you see, at the time we did this
generally
thing.
P2, you mean?
Generally P2. But there are correspondences also for K3s and stuff like this. The point here is that at the time we wrote the paper, what we didn't have was the Bayer-Macri divisor. I mean, really the people who proved the correspondence in general is Bayer-Macri. I mean, I think if you combine our work with that Bayer-Macri thing, more or less, then you get it. But the people who wrote it down is Chunyi Li and Xiao Lei Zhao. The key point here is that we didn't have the Neff divisor. So that paper appeared after we had done this thing.
is that it?
Yeah, I think so. I think I've been going over already, so let's just. All right.
Are there any questions?
Yeah. Yeah, I mean, my question is whether any variety that peak is not set, I mean, it's a variety.
Okay.
So you have also some kind of stratification in the neurons-Severity group with the polarizations that define 9 small spaces.
Yeah.
I mean, using BGIT, you have some stratification.
Right.
Here also you have the Mori stratification, and then you have the Bridgeland stratification.
Right. There, you can view the VGIT stratification in terms of the Brisland stratification, and that's a paper of certainly Bertram is one of the. Bertram is certainly one of the authors of that paper. It's Christian is the other one, right?
Right, Christian
Martinez, and then there's somebody else involved. There is a paper. There is a paper that I think involves at least these 2 authors, and as I recall, one more person, but I'm blanking on the name now, where they actually tell you how to do the VGIT from the Brisbane point of view. So you can look at that paper. And I don't remember exactly in what generality they do it, but maybe.
I think it's only for P2 also.
Is it only for P2?
No, but
It might be
P2 is
more
only
general
if you only
than.
have
No,
one
I think
polarization.
it's more general than that. I don't know.
You need a variety that has more.
Yeah. I mean, I think they just. So maybe the names are not right, but I'm pretty sure that Bertram is one of them. Yeah. So if you look on the archive, like they have a thing about moving the ample and viewing this thing in terms of.
Yeah, because I
in
always
terms of
wonder how
Bridgeland.
the relation between-
Yeah, you can do that, and I mean, I can look it up afterwards and
Don't
tell you what the
worry, I will
paper
look.
is, but.
Okay.
Do you have any comment on these divisors or these table-based loci being irreducible or not?
Oh, no, they're going to be reducible in general. Like, for instance, like, when you hit that thing, right, it's not true that, for instance, already like 7 points lying on a conic and 4 points lying on a line, right? Those are different conditions. I mean, you can have 7 points lying on a conic without 4 of them lying on a line, and you can have 4 lying on the line with the 3 not lying on the line, so they won't lie on a conic. So, it's not going to be true that in general, there will be like many components to this base loci, like the base loci that you pick up. And I think that you don't even have to have walls coinciding for that to happen, probably. I mean, you might say that, okay, that's happening is because 2 different walls coincide, but I think that you don't need that. I don't know an example off the top of my head, but
And what about the extremal divisor?
The extremal divisor. So you see, the extremal divisor, right? If you have any extremal divisor, right? The smallest effective member on that ray has to be irreducible.
Okay.
This is not the fact about.
Okay.
This is just the fact about
Okay.
being extremal, I think. Because, because what you're saying is that, say that you have a D extremal, right? If this thing is reducible, you can write it as D1 plus D2. But because it's extremal, D1 and D2 are both proportional to D.
Yeah.
And if you've chosen to be the smallest effective divisor in that ray, then you can't do that. Okay.
Another question.
Yeah.
that is with the Bridging stability, if you have a condition, then you get a moduli space.
Yes.
How do you construct that moduli space?
Or how do you
Yeah,
construct? Well, when you get the moduli space, you have to be a little bit careful. You get it as an Artin stack or something like
Well,
that.
okay. It's not usually with GIT, so
No.
what kind of things?
I think in general, all we know is that you have an Artin stack. I don't think that we know that there's necessarily
Nothing associated.
Yeah. There are special things that happen for certain surfaces like P2 or K3 surfaces, things like this, right? For P2, you can construct these things by GIT, and that's, we remarked that how you do that.
That is the relation between the BGIT and the Bridgeland. If the moduli space are also constructed with GIT.
But I think there the statement, the theorem is something like, say that you change the polarization, you hit a wall.
Yeah.
And then when you hit the wall, you get some birational thing on the other side. Then somehow there's a way of viewing this birational transformation as a Bridgeland transformation.
Okay.
I don't know. I forget what are the assumptions on the theorem. So you have to look it up. It's possible that, I don't know whether they had to assume that you need to have projective moduli spaces or something like this. The other thing that you can do on the case, one thing that I didn't say is that, okay, so maybe the question that you're asking is like this. So there is something called the Bayer-Macri divisor. And what that does is that, you can take the positivity in the Bridgeland definition, and you can associate to the moduli space a divisor, which is positive. But it's only nef. You don't know that it's ample. There are some surfaces for which then you can go ahead and check that it's ample. So what they do is that you turn the positivity in the definition of Bridgeland stability to nefness of the divisor. Okay? So what they do is they construct a nef divisor on all these.
Okay.
You can use this to compute the ample cone of these moduli spaces first. This was something I didn't talk about. Let me maybe write down the formula for you if I have it immediately in my notes. Sorry, I just let me see. Here is what you do. So what you do is you define a linear function. Say that you have any family S, yeah, with some object. These are Brisbane stable objects. And you need to make sense of these things in the derived category, but with the does, okay? So then what you can do is that you can define a functional on curves. Right? So that what that means is that on curves on S. So that if I have a curve on S, I can give you a number. And then furthermore, this number will be non-negative. And then you can view as a functional on curves as a divisor class. Okay? So what you do is like this. So it will depend on this Brisbane stability condition. This is your Brisbane stability condition, and it depends on this family. So, if you have universal families and stuff like this, then you know what it means. If you don't have them, then you need to sort of jump up and down and say stuff about, okay, but we don't worry about that. Let's pretend that. So what you do, the way you define this thing is that you do the imaginary part of what you do is you do the Fourier-Mukai transform with respect to this universal family of the structure sheaf of C. Right? Then you have the Z associated to this, right? Which is my Brisbane stability is this, and you divide it by the, Z of your object. Z of your object. And maybe there's a minus sign you put someplace, maybe a minus sign.
The Fourier-Mukai is with respect
to the universal family. So you pull back all C, you tensor it, and you push it back. Yeah, on C cross.
Okay, so
you relate both. That's right. And then you see the point of this thing is that the point of this thing is that like this, the positivity in Brisbane stability is basically says that this number is non-negative always. So that what you get is a Neff divisor. Yeah. And you can also characterize the curve that has 0. Right? And then the theorem of Bayer-Macri is something like this. So a curve is equal to 0 if and only if the objects parameterized by that curve are S-equivalent.
S-equivalent?
Right. I mean, or at least the general two objects it's parameterized by those things are S-equivalent.
Yeah, they are going to be the...
But now you see, if you want to show ampleness, you need to work a little harder. Yeah. I mean, even if you don't have curves of S-equivalent things, you see, it's not quite enough to say that all intersections with curves are non-negative to say that you are ample, right? There's some minor differences there. And then, on some surfaces, of course, you can do it. Because, I mean, other things, like, if you have a K3, then this thing is whatever hypercalar, you have extra structure, stuff like this. Sometimes you can also recognize these things, yeah? Like, they are determinantal bundles at the end of the day. So, like, the Donaldson construction, you can view it as, you can compute which Donaldson bundle it coincides with, yeah? And then from there, sometimes you know that it has to be ample or things like this. But so there are things you can do.
Oh, that's a good idea of the Fourier-Mukai.
Yeah.
That's true.
Okay. Yeah. No, I think that probably the most important use of Brisbane stabilities actually comes in this birational geometry thing and telling the ampleness, because that we don't know how to do classically. I mean, all these things, at the end of the day, I'm telling you that there's one-to-one correspondence between the classical picture and the Brisbane picture. But this one, I don't know how to do classically. I mean, it's really turning that positivity. I mean, it's somehow milking exactly the Bogomolov inequality and the Hodge index theorem the right way. So, like, presumably there's a classical translation of this thing, but I don't know how to do it. I think you make too many translations to trace it back. I mean, there's also, I should say that to this, there's Abramovich Polishchuk should be mentioned as well. Abramovich Polishchuk. How do you spell Polishchuk? Okay, I think maybe I have too many. Polish, something like that, yeah. Too many. You're not recording, are you? So you know, there is the key construction like that makes this kind of thing work is actually due to that. But
Oda also. Oda?
Oda?
I think that he also made some construction.
Oh, I'm sure they I'm sure. I mean, yeah.
Following up with the question of Leanne, can you say a little bit about what shows up in the first chambers in the stable base locus decomposition?
Yeah, I mean the first few chambers, you know exactly, like you know.
But not in this direction. That you did.
Oh, this
Exactly.
direction? No,
Exactly.
no, that direction, you know, there's all sorts of bundles are appearing, and you need to know like things that fail to impose independent conditions in these higher and higher rank
But
bundles.
for instance, the movable class always has the stable base loci of that always has codimension 2 or higher.
The movable class.
The extremal one.
No, I mean,
I guess there's no reason.
no, I mean, you know,
Codimension 2, but
yeah, I mean, for instance, if you look at just 2 points, right? The movable class and the ample class, then the Neff class coincide, and that's base point 3, for instance.
okay. All right. Well, if there are no more questions, let's thank Izzet again. Thank you for very beautiful lectures.
Well, thank you for, you know, making this happen, you know. Yeah, maybe we should thank César actually for organizing all these things.
Yeah.
And I don't know who else is actually involved in organizing. It's Laetitia, so we thank Laetitia too, you know. And all of you for coming, you know. So.
The people who
Yeah, why not? Why not?
No,